Welcome to the DAK Machine Safety Podcast. We support the development of a safer, sustainable workplace. In this podcast episode, we will close the series on operational excellence. We remind listeners that productivity, quality, and safety should be fully integrated for true operational excellence. This series focused on identifying and mitigating risk using available safety tools and methods. This process will necessarily identify variables that may be unknown to management. Identification of unknown variables provides the opportunity to implement feasible risk reduction and opens the door to making the work faster and easier in the process. Listeners are also reminded that while alternative methods to control hazardous energy are only one form of risk reduction, it was the focus of our podcast series because machine lockout is often misunderstood. In this final segment, we will use case study examples to better understand how alternative methods and the proper application of lockout can help in the workplace. We close out the podcast with a quick reminder of some of the more important podcasts that led to this point.
Do you have a case study that applies broadly in manufacturing?
Yes. Remember the OSHRC Review Commission West Vaco decision in 1993? The commission ruled that setting up a machine for a new production run was service and maintenance requiring lockout. Tasks commonly called setup or changeover require energy using circuit functions on the control panel, also called an HMI or human-machine interface.
What would be the impact of trying to do the task under lockout?
One recent example arose when OSHA inspected a facility and advised the company that lockout was required for a changeover to a new product run on an injection molding machine. The company had to hire a third-party expert to assist with the analysis. The task-based risk assessment showed 25 steps. The current time to perform a changeover using control panel functions was approximately 20 minutes. LOTO would double that, requiring at least 40 minutes per changeover.
Can you provide more information on the increased time needed to set up?
Yes. Lockout by both operators would have to be performed 6 times during each mold change. Each lockout would require 2 trips to the disconnect, one to shut down the power and lock the device, and the second to go back and restore power for the next step. After each lockout, it took 2 1/2 to 3 minutes for the machine to be ready for the next step, while the control panel restored itself.
Were there other issues that would be part of documenting feasibility?
Yes. Based on the experience of the third-party expert and the mechanic, problems with machine startup and malfunctions would likely occur after restoring power. Computers sometimes react unpredictably when power is removed. The ergonomic impact of lockout was insignificant. However, unnecessary walking to and from the disconnect increased the risk of slip, trip, and fall, and would stress the operators who were trying to complete a task in a timely manner.
What about the control reliability issue?
Control reliable circuits on the injection molding machines were designed with multiple redundancies such that failures within the circuit would not result in unexpected or unintended energization that could create a hazard. 5 interlocking devices coupled with another 3 control functions, modes of operation on the control panel, made it so that the machine would fail to go to a safe state.
What was the conclusion?
Using criteria from B11 locking the primary energy source was documented as not being feasible. The current safeguarding system complied with OSHA requirements and achieved acceptable risk.
Could our machine suppliers use this thinking to develop special modes of operation to facilitate efficiency and safety during normal production?
That is a great question, and the answer is yes. Clause 7 of B11 contains, when an engineering control has been manually suspended during the manual and special modes, alternate risk reduction measures shall be required, as determined by a risk assessment. The informative note to Clause 7 states, special modes are specific to a given task and provide the necessary power source and safety function by their selection. Particular attention should be given to removing hazardous energy from adjacent machines or auxiliary functions, which can create a hazardous situation.
Are there any other examples?
Yes. This was featured in ASSP's Professional Safety Journal. The peer-reviewed article, The myth of zero energy and its negative impact on prevention through design featured a good example of a production operation where the company did not differentiate between hazardous and non-hazardous energy. Perceiving a greater level of safety for the workers, the company elected to require zero energy and shut down the energy to a glue pot while workers adjusted or cleaned the mechanism for feeding the wrappers in a packaging machine.
What was the result of isolating and locking the glue pot?
It took 2 hours for the glue pot to cool and reach ambient temperature. Due to the solidification of glue, the feed line and pump required cleaning before startup. For each stoppage, 2 to 3 hours of production were lost.
What was the solution?
Once the company correctly identified the hazardous energy and differentiated it from the non-hazardous energy, a worker could complete the task in 5 to 10 minutes using lockout of only the hazardous energy.
I'm a little confused. Was that an alternative method or just a proper lockout?
That is another excellent question and one that shows great insight. In this second example, the proper application of lockout did not require an alternative method. What's important is that the thinking used for alternative methods facilitates selecting a proper risk reduction method, such as isolating and locking only hazardous energy.
So, you are not trying to suggest that we use only alternative methods and not lockout. Is that correct?
When isolating and locking a primary energy source is feasible, lockout should always be used. An alternative method should be selected for service and maintenance tasks requiring power. If you try to impose a safety rule or policy that will not allow a task to be done, it is almost certain that workers will ignore it. In such situations, you have left them without any protection, and the risk of severe or fatal injury increases.
Are there any other examples?
Yes. Let's return to the example of a single robot cell where an authorized worker had to enter periodically to make tool changes.
Okay. But first, please clarify if this case would be a tool change to which the minor servicing exemption to 29 CFR 1910 147 applied, or would it be an alternative method to lockout?
For once, we can simplify things. It doesn't matter. The company wanted to develop a safe operating procedure posted at the point of use. Whether the task was minor servicing due to being routine, repetitive, and integral to production, or an alternative method would have been a matter for the lawyers in OSHA. In the real world of work, and from the worker's perspective, it didn't matter. It was a safe operating procedure.
Refresh my memory on this example.
This was a single robot cell loading and unloading parts into a CNC turning machine. A printout told the worker when a change of tool was required. Entry into the cell to perform the task did not require any work nor exposure to a hazardous motion of the robot.
What was the problem?
The engineers believed that all power in the cell had to be shut off without isolating and locking the primary energy sources.
Okay, but what you're saying doesn't involve lockout, correct?
Correct. Remember, the issue is not lockout, but the control of hazardous energy. That confusion is not OSHA's fault. The plain language of 29 CFR 1910 147 makes it very clear that the regulation deals with controlling hazardous energy. Safety professionals and engineers have just latched on to the term lockout.
Why did the engineers believe all power had to be shut off, even if lockout wasn't involved?
The answer was, and I paraphrase, that's what we were told to do. Under questioning, these very experienced and competent engineers could cite neither the source of that direction nor any law or standard that dictated shutting off the non-hazardous energy of the gripper.
What was the issue?
The gripper robot would drop the small part and ruin it. Yet the power to keep the part held in the gripper posed no hazard for the task being performed. It was non-hazardous energy.
I initially thought that this was a definitive process that yielded black and white answers.
I'm sorry, but this is a complex world with complex laws and many variations between different companies. We aim to give you the competence and confidence to stand by your results when challenged. There are no shortcuts, but the result will be worth it. both from a risk reduction perspective and productivity improvements.
What should I take away from this podcast series?
We've tried to introduce you to the concepts of operational excellence and how lean thinking, respect for people, and the teachings of Dr. Deming can help improve productivity, quality, and safety. Throughout the series, we focused on alternative methods in lieu of traditional lockout. We hope that knowledge of available tools and methods will encourage listeners to use risk assessment and feasible application of the hazard control hierarchy to tackle real-world issues in their organization. With the input and collaboration of workers and engineers, it is possible to have workers perform necessary tasks with acceptable risk. Thanks for tuning into this episode by DAK Machine Safety. Today we closed a podcast series on operational excellence. You can support us by clicking like and subscribing. Take care, everyone, and until next time.